Hello, my name is Gaurav Kumar. My teammates are Emily Lin and Mayur Singh, and we'll be presenting our process and findings of the internal combustion engine lab. For this lab, a client has tasked the team with optimizing the performance of their engine. The engine is an internal combustion engine capable of operating with compressed air or propane fuel. In order to optimize the engine, the system parameters must be identified first. Using the parameters, the engine can be tested and analyzed in respect to its 4 strokes. During experimentation, the engine was coupled to a motor which can turn the engine. The position data was collected using an encoder. Meanwhile, the torque data was collected using a force transducer. Week 1 of the lab consisted of system ID. Weeks 2 and 3 validated the model under 2 different conditions. Lastly, week 3 also optimized the engine performance with pressure injection timing. All the experimental analysis was performed with the work energy balance.
During week 1, we must perform system identification of our engine. We need to determine our torque gain, the inertia of the flywheel, motor work, and frictional work. Our operating conditions for this week is that the head of the piston is off, so there is no air work, and there is no combustion, so there is no pressure injection. To find the torque at the 3 engine settings for this week, we need to calibrate the torque sensor. This is done by linear regression using voltage data from our force transducer and using various weights to obtain a calibration torque. Using this, we can find a gain which we'll use for all further calculations. To calculate the work done by the motor at each of the 3 speeds, we need to make assumptions about the steady state operation of the engine, including that the work at A is equal to the work at B, the work done by the piston is 0 joules, the work of air is 0 joules. We use numerical integration to calculate the work of the motor over 10 degrees, and we also use our energy balance to find the final value of the work done by the motor. For the low speed, it was 126.6 joules, for the medium speed, it was 249.9 joules, and for the high speed, it was 354.9 joules.
An important parameter of the system is the inertia. Applying assumptions and rearranging the work energy equation for accelerating data, the experimental inertia was 0.02 kilogram meter squared with the flywheels and 7.15 10 to the negative 4 kilogram meter squared without flywheel. It's important to consider no flywheel inertia because all the links and gears in the system still impart inertia during the experiment. With a theoretical inertia of 0.0187 kilograms meter squared, the experiment yielded a percent error of 3.13%.
Some of the goals for week 2 are to evaluate a model of 4-stroke cycle without combustion and subsequently performing a work kinetic energy analysis on it. And a second goal is to analyze the condition where air work exists and no pressure injection is present. Afterwards, the goal will be to determine the validity of the experimental model. The calibration curve was redefined for the week 2 dataset. The gain for the calibration curve was 0.7667, which was used for future calculations of the motor torque for each set of data. The following graphs compare the low, medium, and high speed cases with either the one flywheel or all flywheel system. Some main effects of mass that can be seen is that there is a decreased torque as mass is added to the high speed case. There is also slightly higher torques for lower speed than higher speed for the all flywheel case. Some observable effects of speed include more torque peaks and increased noise at lower speeds for a given angular position range. Also, there are increased difficulty to detect different strokes at high speeds. The effects of mass can also be seen with the angular position versus torque for the low speed case. With the all flywheel case, for example, a larger angular position interval can be seen between each compressive stroke compared to the lower mass case. The intake, compression, expansion, and exhaust strokes are highlighted in the figures, which agrees with the fact that each stroke occurs over 1 pi radian. The effects of speed can similarly be observed by analyzing the one flywheel configuration with different speeds, the medium and high speed setting. It can also be seen that for the medium speeds motor torque versus time graph, the torque differences are distinguishable, whereas for higher speeds, it is more difficult to detect and analyze each stroke. It is easily seen, however, that for higher speeds, the torque is also higher in magnitude. The air work can be calculated from experimental results, as shown in the energy balance equation. The piston and air work terms are assumed to be 0, while the frictional work can be determined experimentally, and the motor work can be found through integration methods. Afterwards, the difference in kinetic energy can be calculated between each stroke, which can be plotted as shown. It can be seen that the kinetic energy at the end of the expansion stroke is the lowest. Also, most of these curves reach zero by the end of the exhaust cycle, except for the all-flywheel high-speed case. The volume versus angular position graph can also be plotted, where the low, medium, and high-speed cases are graphed to compare mass and speed effects. The higher speed occurs for a higher angular distance, and even more so with the lower mass. After the stroke analysis, some results were tabulated. The experimental results for each stroke were determined with W-air calculated at each pi interval. The model results can be found using the compression work equation, while the expansion stroke is the negative of the compressive work. The intake and exhaust strokes have a W-air value of 0 since the flow losses are negligible as air is drawn into the system. The theoretical compressive W-air can be calculated to be negative 7.0532 joules, with the expansion W-air being its negative. From the experimental results, it is evident that the expansion curve has a very low and negative W-air value for all runs, contrary to the supposed theoretical value. The compressive intake and exhaust strokes show trends that are more correlated with the model values, and overall there are some deviations from the theoretical result, especially for the expansion stroke, and as such the experimental total work is also more negative in value. The error can potentially be attributed to excessive noise when running the experiment.
Week 3 models the system with the cylinder head on. Pressure will be injected during the power stroke in order to simulate combustion. The torque sensors to be calibrated again for accuracy. Then the difference in the theoretical and experimental models is to be compared to uncertainty for model validation. Ultimately, using the model, the different pressure injection times are to be studied so that performance of the engine is optimized by finding the ideal pressure injection times. As seen in week 1, the motor work can be calculated by numerically integrating the torque in respect to the angle. Meanwhile, the steady-state torque is used to calculate the frictional torque for each stroke. The angular velocity can be calculated using the data for angular position versus time. Meanwhile, the moment of inertia was calculated in week 1 as a part of system ID. After utilizing the known inputs, the experimental air work can be set in terms of the motor work, friction work, and the change in kinetic energy. After determining the experimental air work, it's important to evaluate the theoretical model. Due to the opening of the intake and exhaust valves, pressure is assumed to be atmospheric for the intake and exhaust stroke. Therefore, air work will be 0. During the compression stroke, the system undergoes adiabatic compression, meaning no heat loss. The air work can be calculated by integrating the gauge pressure in respect to volume from start of the compression to the end of the stroke. Lastly, the pressure at the end of the stroke can be calculated using the adiabatic condition where PV to the gamma is constant. The power stroke takes place in 3 stages. After the end of compression, the piston undergoes adiabatic expansion. Then, at a specific angle, pressure is injected into the system to simulate combustion. During this stage, the engine undergoes isobaric expansion. The volume at the beginning and the end of the isobaric expansion is obtained with the angle at which pressure is injected and stopped. Using the angle, the piston height can be calculated and then converted to volume. It's important to note that pressure injection is delayed initially because right at the beginning of the power stroke, the crankshaft is vertical, meaning the pressure wouldn't be able to impart any torque until the piston moved down a little. Lastly, once the pressure injection stops, the rest of the stroke follows adiabatic expansion until bottom dead center. Integrating the pressure in respect to the volume, the air work can be calculated for each step of the expansion. Ultimately, the theoretical air work can be calculated by adding the air work for each of the 4 strokes.
The main uncertainty we want to find for this week is the motor work uncertainty. To find that uncertainty, we need a bunch of other uncertainties, including the force transducer voltage uncertainty, the angular position uncertainty, the caliper, calibration torque, and average torque uncertainty, and the angular velocity uncertainty, to name a few. Lastly, we can plug all these values in to eventually obtain our work uncertainty, and from there we can find the motor work uncertainty in the bottom formula.
After evaluating the air work experimentally and theoretically, the 2 values can be subtracted in order to determine the work error. This is the error caused by unmodeled parameters. This value is then compared to the motor work uncertainty to determine if the work error is due to uncertainty or an invalid model. If the work error falls within uncertainty, the model is valid. If it doesn't, the model is invalid.